Shall we start? Hello, shall we start? Good morning, all. Shall we start? Yeah, fine. Okay. So in the previous class, we just dealt with the design methodologies, top down and bottom up approach. So now let us try to see the same with the help of a video. We'll try to see what do you mean by top down and bottom up design methodology. More in general, previous class we I just given you an example of T flip flop, that is a 4-bit triple carry adder using T flip flop. So same T flip flop was achieved by or designed using an inverter and a D flip flop. So let us try to elaborate that with the help of video. I'll just share you the video. Just watch this video. After that, we'll comment on this.
Methodology, differences between modules and module instances, parts of simulation, design block, and stimulus block. Before I dive into my circuit to build a higher level system, down into simpler tasks, and finally till it reaches the simplest cell, which is called as the leaf cell. In the bottom-up design methodology, we start with the simplest cell available to us, that is the leaf cell. Using these leaf cells, we build the higher level cells called as the macro cells. And using these macro cells, next higher level blocks are formed. So here the level of the in the figure only one level of macro cells is shown, whereas the number of levels for the macro cells can be any until you reach the top level block. Typically, a combination of top-down and bottom-up flows are used. The design architects define the specification of the top-level block, whereas the logic designers decide how the design is to be structured by breaking up the functionality into blocks and sub-blocks. At the same time, the circuit designers are responsible for designing optimized circuits for the leaf cells. They build higher level cells by using these leaf cells. Somewhere in the intermediate place, the two flows will meet, where the switch level circuit designers have created a library of leaf cells using switches. By switches, I mean transistors. So and the logic level designers have designed from the top down until all modules are defined in terms of leaf cells. So these logic designers work at the gate level. We'll look into an example to understand the bottom up and the top down design methodologies. The example taken is 4-bit triple carry counter. The 4-bit triple carry counter is realized using 4 T flip-flops, and it is ripple carry counter, that is it's an asynchronous counter because only the first flip-flop will be getting its clock from the system clock. The second flip-flop will get its clock from the output of the first flip-flop. The output of the second flip-flop is given as clock to the third flip-flop. The output of the third flip-flop is given as clock to the fourth flip-flop. And you can see that there is a bubble for the clock input. This indicates that it is a negative edge triggered. A bubble and a arrow inside the square indicates that it is edge triggered, and bubble indicates it is negative edge triggered. So the meaning of negative edge triggered is only for the negative going transition of the clock. That is, when the clock makes a transition from 1 to 0, the flip-flop will be active. And as per the characteristics of the T flip-flop, when the T flip-flop gets an active clock, it toggles the output. Meaning, when the flip-flop gets the active clock, the Q will, if the previous value of Q was 0, it will become 1 now. If the previous state was 1, on getting an active clock, it will become 0. And you can see the reset signal is active high, and it is given to all the flip-flops. The outputs Q0, Q1, Q2, Q3. Here Q0 is the least significant bit and Q3 is the most significant bit. We'll look into the working of the ripple carry counter. For your reference, I have included the logic diagram of the 4-bit ripple carry counter. So here there is the timing diagram of the same. So first input is the clock. So clock is a continuous train of pulses. Then the outputs Q0, Q1, Q2, Q3 are plotted accordingly. So here you can see the first flip-flop will get this clock input. That is continuous train of pulses. That is the system clock. Now, whenever this clock goes through a negative going transition, so before that, for initial state, we will take we'll reset the counter, hence all the outputs will be 0, 0, 0, 0. Now, the clock will have its first negative going transition at this point. So, at this point, the first flip-flop will get its active clock. So when it gets its active clock, the output will toggle. So previously it was 0. So now it will toggle and become 1. Next, this flip-flop will get the active clock at this point. So that time the previous state was 1. Now it will toggle and become 0. So for every negative going transition, you can note that the negative going transition is made slightly bold. So for every negative going transition, it will toggle from 1 to 0 and 0 to 1. Now coming to the second flip-flop with output Q1. This will get clock from Q0. So here initially this is positive going transition, so nothing will happen. The first negative going transition of Q0 is at this point. So at this point, this flip-flop, that is the second flip-flop with output Q1 will get an active clock. So when it gets an active clock, it will toggle the output. So initially the Q1 was 0 and on getting a negative edge clock, it will become 1. So for every negative going transition of Q0, it will toggle. So for every 2 clock pulses of Q0, this will toggle. Similarly, Q2 will toggle only when there is a negative going transition on Q1. So here you can see this is a positive going transition from 0 to 1. So nothing happens here. For the negative going transition here, the Q2 will toggle. Similarly, another negative going transition, Q2 will toggle from 1 to 0. Likewise, Q3. Q3 will toggle only when it gets a negative going transition on Q2. So Q2 will have its negative edge transition at this point. So here the Q3 will toggle from 1 to 0. Now you can see the outputs at any instant. As I told you, Q0 is the least significant bit and Q3 is the most significant bit. So the outputs at any instant, you should read it vertically. So it will be first instance, it is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and so on up to 1, 1, 1, 1. Then all will get the negative transition, going transition at this point. So all will be reset to 0. This will continue to count from again 1, 2, 3 up to 15 and the cycle repeats. Based on the timing diagram explained in the previous slide, I have the truth table of the 4-bit triple carry counter. So here in the truth table, you can see that Q0 is toggling for every clock pulse, because for every clock pulse there will be a negative going transition, and Q1 will toggle only when Q0 goes from 1 to 0. See here again Q0 is going from 1 to 0, Q1 will toggle. Q2 will toggle only when there is a 1 to 0 transition on Q1, say here, and also say here there is a 1 to 0 transition, so Q2 will toggle. Similarly, Q3 will toggle only when there is a 1 to 0 transition on Q2. So this is the truth table of the 4-bit triple carry counter. We look into how we built the component module, that is the T flip-flop. This is the truth table of the T flip-flop. Here there is this reset input. The reset input we have taken as active high. Active high means when the value of that reset is 1, irrespective of the previous state. Qn is previous state, Qn plus 1 is the next state of the flip-flop. So when the reset value is 1, irrespective of the previous state, the next state will be 0. Whereas for the inactive state of the reset, that is inactive value of the reset, that is when reset is 0, 0, when the previous state was 0, the next state will be toggled, that is it will become 1. If the next state was 1, it will become 0. Let us see how we have built the T flip-flop. The T flip-flop is built using a D flip-flop and a inverter. So as you know, the D flip-flop is when it gets an active clock, whatever is at the D input will be passed on to the Q output. So here what we have what modification we have done is the output Q, we have passed it through an inverter and given it to the input D. So here this will behave like a T flip-flop. So when the clock is active, that is when the clock is going from 1 to 0, whatever is at the input. So if the previous state was 0, it would have inverted and come here. So now D is 1. So as per the characteristics of the D flip-flop, it is passed on to the output Q. So previous state was 0. Now the current state will be 1. Similarly, if the previous state was 1, the next state would be 0. So for the inactive edge of the clock, nothing will happen. The state will remain same as the previous state. Thus we put this 4-bit triple carry counter in the top-down and the bottom-up design methodology approach. So here, the ripple carry counter forms the top-level block, which is further divided into component modules. As we have seen, the ripple carry counter is built using 4 T flip-flops. T flip-flop becomes the sub-block of the top block. So here, this is the intermediate level. T flip-flop can be further realized using D flip-flop and a inverter gate. So each one is subdivided into these two component modules. So this is how we specify the top-down methodology. Further, we could build the D flip-flop in the, if we think of the bottom-up design methodology, we could build the D flip-flop using AND gates and OR gates, or you could have built the D flip-flops using transistors, which forms the leaf cells. So the bottom-up and the top-down approach meet at the D flip-flop level. In this video, we have seen what are hierarchical design concepts that
Okay. We just seen the design of top down and bottom up approach. I hope you have got the concept. So at this point, don't worry that so artha agilla antandre fine, no problem. You are in the right place. If you are not understood the concepts, then you are in the right place anta. Why? Because at the beginning point of time, we are not aware of programming, guys. Yeah, things need not to be understood at a glance. So my suggestion is that go through the notes once again, so you'll be familiar with the concepts. So so this completes your first module. So before completing, we have one small concept. Let me explain that. That is design block and stimulus block. Then we'll complete our first module. Yeah, coming back to the actual syllabus. Yeah, these are all we have seen. Let us now try to see how a module looks, how a general format of module is there. So you can see here, this is the module. A module is a basic building block in verilog. As we are aware that what is a module and all, I'll not take much time on this. A module can be an element or a collection of lower level of design blocks. Elements are grouped into modules to provide common functionality that is used as many places in the design. So you can name a module, like the example I've shown. Module, I have shown in blue words, the blue letters indicates that it's a keyword. Module name, module terminal list, then module internals. The final is here end module. So just I've given example of module T flip flop. Module name is T flip flop, and the internal terminal list are Q, clock, reset. Then we have the functionality of T flip flop, end module. So Verilog is both behavior and structural language. Internals of each module can be defined at 4 levels of abstraction. So we can define a module in 4 ways. 4 ways or 4 levels of abstraction. So better we use this term levels of abstraction. Levels of abstraction means it can be any of the four: behavioral level or behavioral or algorithmic level. It is very similar to C language. We just define the behavioral model. Data flow level. The designer is aware of flows, how the data flows between hardware registers and how the data is processed in design. Then we have the gate level. Gate level is somewhat okay. You can write it using only gates. The model is implemented in terms of logic gates and interconnections between these gates. Design at this level is similar to describing a design in terms of gate level logic diagram. So looking at the logic diagram, we can write the program. That is your gate level design. Switch level, lowest level. It is the lowest level a model can be implemented in terms of switches. So this is one of the difficult level. This is one of the difficult level of abstraction. So we have 4 levels of abstraction. A program can be written in 4 ways or 4 different levels of abstraction. One is what is that? The first one is behavioral or algorithmic level. Second one is data flow level, behavioral algorithmic level. Second one is data flow level. Third one is gate level. And fourth one is switch level. Switch level. Verilog allows the designer to mix and match all the 4 levels of abstraction. You can mix and match it. In digital design community, the term register transfer level is frequently used for a Verilog description that uses a combination of behavioral and data flow constructs. And it is acceptable. You can mix the different levels of abstraction and write the program. So once you write the program, once you start writing the programs, you'll come to know the advantages of Verilog. The higher the level of abstraction, the more flexible and technology independent is the design. Lower the level of abstraction, design becomes technology dependent and inflexible. I said switch level. So in switch level, you have to use only the transistors, that is NMOS and PMOS. If you are going for a CMOS design methodology, you have to design the entire program using the NMOSFET and PMOSFETs. Example, coding in C is very easy versus assembly language program. Assembly language programming, you need to remember many mnemonics and you have to write the program. Whereas coding in C is quite simple. So instance, we call this instance. A module provides a template form, a template from which you can create actual objects. So when a module is invoked, Verilog creates a unique object from the template. This unique object is the instance. Each object has its own name, variables, parameters, and IO interface. The process of creating objects from a module template is called instantiation, and the objects are called as instances. Example of instance, consider 4-bit triple carry counter. The top level block creates 4 instances from the T flip-flop. So if you just consider this 4-bit triple carry counter program, top level module is called as triple carry counter. It has 4 T flip-flops. Once you write that program, Verilog itself will invoke or it will create the instance. 4 T flip-flops. Each T flip-flop has a D flip-flop and inverter gate. So which in turn T flip-flop has an inverter and D flip-flop. So each instance must be given a unique name. Each instance must be given a unique name. So the program like this: model triple carry counter, Q comma clock comma reset, output. So this is how we define the vectors here. 4-bit vector 3:0 means what? It involves Q0, Q1, Q2, Q3. So output 4 bits. So we'll write it in square. We'll start with the square basis. 3:0 for 4 bits. Similarly, if it's 3-bit, we'll write 2:0. If it's 2-bit, 1:0. Likewise. Input clock comma reset. Input are only 1 bits. That's why we'll write just input clock comma reset. 4 instances of the model T flip-flop are created. Each has unique name. Each instance is passed a set of signals. Notice that each instance is a copy of module T flip-flop. So T flip flop is written one. Now you will write the instance name. First T flip flop. So we'll write T flip flop is the actual module. Instance name is T flip flop 0. The outputs are Q0, clock, comma, reset. So similarly, you have the next instance T flip flop 1. Outputs are Q1, Q0, reset. Likewise, we'll write the four different T flip flops with four different instances naming T flip flop 0, T flip flop 1, T flip flop 2, T flip flop 3. End module. Now, how to define the T flip flop? Whenever define this module T flip flop, now we have to define the module T flip flops. How T flip flop is written as module T flip flop. The outputs are clock, comma, sorry, Q, comma, clock, comma, reset. Output Q, input clock, comma, reset. Wire is D. Now, T flip flop is created using a D flip flop. D flip flop, D flip flop 0, Q, comma, D, comma, clock, comma, reset. Now you can see here this T flip flop has instantiated the D flip flop Q, comma, D, comma, clock, comma, reset along with NOT gate, NOT N1 D, comma, Q. NOT gate is a Verilog primitive, so we need not define NOT. So primitives are already present inside this language, which we need not define once again. That's it. End module. So this is what is your program for 4-bit ripple carry counter and the instances. So now remember here we are writing a top module. Top module is called as ripple carry counter, which will instantiate 4 tip flip flops. Similarly, 4 tip flip flops are instantiated. Once they are instantiated, T flip flops are made by T flip flop and inverter. T flip flop model will instantiate D flip flop and inverter. This is the meaning of instances in Verilog. Instance in Verilog. Then parts of simulation. So one more important point. In Verilog, it is illegal to nest modules. Sir, can I write a module inside a module? No. Once a module is written, module T flip flop. Once again, you cannot write module D flip flop inside that. Module, you cannot nest modules. One hakangilla. Module D flip flop, write the program, end module. Module D flip flop, start the program, end module. So nesting the modules is illegal. Nesting the modules is illegal. You will get an error. One module definition cannot contain another module definition within the module and end module statements. Instead, a module definition can incorporate copies of other modules by instantiating them. We can only instantiate. You cannot write module inside a module. Yeah, then parts of simulation. After designing a system, it has to be tested and verified for its correctness. Yes, definitely. Once you rig up the circuit in the lab, the next thing is you'll switch on the kit and you'll give the inputs and you'll check the outputs. Just remember your logic design lab, visual system design lab. There you'll rig up the circuit. Once you rig up the circuits, then you'll check the output by providing the inputs and outputs. So it is done like this only. After designing the system, it has to be tested and verified for its correctness. So that correctness, whether the circuit whether the things we have done is meeting our expectation or if my program is wrong or right, I can check using the parts of simulation. That is, the device has to be tested. Two styles of stimulus application is there. So I can write the stimulus program or test bench code. Test bench code. The stimulus block instantiate the design block. So you can see here, this is a stimulus block. Clock reset you have to apply. Then output is Q. Stimulus block instantiate design block. So this is the stimulus block. Sorry, this will instantiate the design block. So you can see here, this is your stimulus block. You are applying the stimulus. Top level block you can see here, D underscore block, D underscore reset, C Q. Design block, clock we are applying clock, reset we are applying reset, Q is the output. Stimulus and design block instantiated in a dummy top level model. So this is how the things will work. So in the video, the same program has been used to explain the things. So this is about your stimulus block and design. So output, so you can see here. So this is your test bench code. Model stimulus, register clock, register reset wire placed to 0 Q. Now we can see here at every 5 seconds clock is equal to now clock. You are toggling your clock here. Initially you are setting the clock to 0. So after 5 seconds, what happens to the clock is it will change it as 1. 0 ಇದ್ರೆ 1 ಆಗುತ್ತೆ. ಇಲ್ಲಿ ನೋಡಬಹುದು 5 seconds 0 ಆಗುತ್ತೆ. Next 5 seconds 1 ಆಗುತ್ತೆ. Like this. After 5 seconds, clock will become not clock. Control the reset signals that drives the design block. Reset is asserted from 0 to 20 and from 200 to 220. Initial begin reset is equal to 1 tick binary 1. 1 tick means it is considering 1 bit. B1 means it is binary 1. We are providing with reset as 1. Next, after 15 seconds, reset will become 0. That we have tried here. After 15 seconds, reset is equal to 1 tick binary 0. After 180 seconds, reset becomes 1 once again. Next, reset is equal to 0. The other 20. Finish. It is 200, I guess, not 20, it is 200. Finish. Terminate the simulation. End. Monitor the outputs. Initial. What you have to monitor? Monitor time, output, Q, end module. Once the stimulus block is completed, we are ready to run the simulation. So output is like this. Initially Q is 0. 20. After 20, output Q is equal to 1. 2 like this. So this is how the things will work in. So you can see here it will count from 0 to 15. Once again it will count from after 15 it will become 0. So here you can see a change here 190. Output becomes 0. 195 because reset is enabled here. Why? Because 180 plus 15, 195. Once again your output is becoming 0. So getting the program. So try to analyze this program. So if you got this, fine. Otherwise, I'll once again explain it to you in the next class. Now the class is open to doubts. If you have any doubts, you can ask me. So this completes your module 1. If you have any doubts, you can ask me. Yes, any doubts? Mark your attendance in the chat window. The class is open, guys. You can ask me doubts. If you have any doubts, you can leave the class. If you don't have any doubts, you can leave the class. Thank you.